Hello and welcome. Welcome to the latest in our series on advanced mixed models. We're delighted to have you join us today. Today we're going to be discussing the application of random regression models. Now then, as always, say hi in the chat, let us know where you're from. Feel free to sort of post any of the challenges or the things that you're looking to get out of today. Any questions and answers, if possible, pop it in the question and answer box. We will attempt to get to all of your questions today. In the event that we can't answer all the questions, we will reply to you via email. There'll be an email going out a couple of days after this webinar, which will give you a copy of the recording, all the associated resources, and anything else that you might need, and an answer to all those questions. Yeah, so do say hi. I don't think there's anything else with housekeeping. So without further ado, I will pass you over to our resident expert, Salvador Gezan. A ti.
Hello, good morning, good afternoon, or good night, depending where you are, once more. Happy to be here. Today, I'm going to talk about random regressions, and I really need to warn you that this is a more difficult topic. I will give a little bit of a varnish of what happens and what are the ideas behind random regression is and how we can use them for breeding. And also, obviously, I will work through an example that I have here. There'll be some math and there'll be some intricate definitions and transformations and things like that. All, again, with the logic of trying to give you an idea of how this technique works. So I'm going to share my screen because, as usual, I have a few slides. I wonder if you can see my screen there.
Looks good.
Okay, so let me just move a few things that are too much on my view. So this, I'm going to, as I mentioned, I'm going to talk about random regressions with some applications to breeding, but I have to go back to the proper definitions of what the statistics is. So the first thing is we talk about random effects regression or random effects coefficient regressions. And if you remember some of your basic statistics, obviously we fit one linear regression, but in this case, we're going to fit multiple linear regressions all at once and something that we call regression with groups. And you can think about something like having a different line for each of your treatments or each of your genotypes. And obviously, these lines don't have exactly the same slope, don't have exactly the same intercept. And the difference between the different lines, obviously, will summarize some of the difference between the different treatments. Now, we move this one a bit farther, and we have groups of observations for individuals, or we can say for genotypes. And those groups of observations have some correlation between themselves, so they are kind of clustered. And for that reason, we're going to start using some random effects. So we tend to say this individual deviates from an overall line with a random intercept and a random slope. And because that individual represents a sample of a potential group of individuals. And this starts already touching a bit on the genetics, where obviously we have random effects for the genotypes. So again, just a simple definition. This is an observation where we have a response for an individual. And I'm going to start moving into the X being some sort of time measurement. So this is random regression. The way I'm presenting it here is related to repeated measures, where the X represents something associated with time. It could be day, it could be hours, it could be regular intervals, it could be irregular intervals, but think about something, days after planting or day after transplanting or something. And so we have the same individual recorded several times. We have an overall intercept that goes through across all the individuals, an overall slope that goes across all the individuals, and a residual error term with some assumptions of independence and so on, which in this case are not going to longer held because we have repeated measures on some of the observations. So what we do is we take that regression, and remember we have the alpha and beta x, and what we do is we extend and we say there is an overall alpha, which is a fixed effect, and then we have intercepts that change from group to group. Think about different genotypes. So you have a genotype that is going to have a different intercept, and that is the AI. So I goes from 1 to the number of genotypes you have. And then we have plus beta, which is an overall slope multiplied by x. But then we also have another little term, which is the BI, which is a small random deviation of that observation with respect to the overall line. So these alpha and betas represent, again, random deters or deviations from what we expect from the overall line from the population. And again, that's what we really want, because those are breeding values, if we're dealing with genotypes, that will represent random deviations from the population. And one important thing is this alpha, or this A and this D, which I wrote in with Latin letters, have variances associated. Of course, they're random effects, so we need to estimate those variances. So we need obviously a population of groups. And the other thing you can think about this is when we write the model, and we'll see, is that we can regroup some of the elements. And notice that this alpha plus beta, alpha is the overall intercept, so it's my 1 in the model. The x is my overall slope with the beta associated, so that's going to be my covariable. Both of these are fixed effects. And then I add random effects. I add the random effect of the individual or the genotype. And then I add a random effect of the individual interacting with the slope, or in this case, time. And that also is going to be a random effect. So then we have the fixed part, and then we have the random part of the model. And that really closes most of the definition of this. Now, one thing that normally you will see is that people tend to assume that these AI and BI are correlated. So because they are adjusted or fitted, if you want, from the same individual or from the same genotype or from the same group, whatever your definition is, then if it goes the slope up, then the intercept goes down, and usually there is a negative or a positive correlation between themselves, and then you need to specify that they're actually not independent random effects, so you need to combine them, and you assume in this particular case that there is a covariance, non-zero covariance between them. You can also model that as a correlation between the parameters. So here is just one example to just kind of warm it up a little bit. This is the same model I show you. This model only has an overall line, but then you can make the intercepts random, which is with the effect of a random genotype, and you can see they move up below that overall line. You can have the intercept fixed, but then you have the random slopes, and then you can see how the slopes change. And then you also have both of them, where you can see that the lines tend to cross and go all over the place. So again, we tend to use this more complicated model with all the terms, okay? So what happens when we do this with breeding data? I know, again, this is usually a long introduction, but so we are going to fit this linear regression to the genotypes. And because it's linear, that will bring a little bit of an issue, because most of the time, these processes that we're studying are not totally linear, so we might have to do some tricks. But in this particular case, I'm saying the genotypes are related to time, age or date or days or whatever, and we're going to fit one linear regression for each of them with random effects. The BLUPs that we obtain are the ones that are going to describe the genotypes. We can obtain many more things to describe the genotypes, but the random intercept and the random slope are going to be very important to even rank the individuals. Think about the random slope. Wherever the individual has the highest positive value, then it's going to actually go much better in terms of rates of growth, for example. But many other things you can have. Now, when we do correlate those effects, we'll have to use this terminology from ASReml, STR, which creates a string of the random effect for the genotype, which is the intercepts or the deviations from the intercept, against the random effect of the genotype by time, which is again the deviation from the slopes. And we need to define a structure for them, which in this case, I'm defining a core H, which means two variances and a correlation for them. So describes perfectly a US or the same variance I show you. This is only two parameters. You can have models that have genotype by time square, or another transformation, whatever you really want, and then you'll have to correlate. In this particular case, if you have a square time, a core H of degree 3, and then you have to put a 3 in there. The ID 22 represents the genotypes, and it says there is 22 genotypes in this particular model. Now, a few more things that happen. The observations are not independent because they belong to the same unit that is being measured over time. And sometimes that's specifically the genotype, but sometimes it's a plot that is the one that is correlated, or a plant ID that is the one that is correlated over time. So you need to model that temporal correlation. Now that it's part of it is absorbed by the other random effects. So we'll have to see how well that works. And this is, again, the nature of this particular case where it's repeated measures. So because the X is time. And we have different ways to model this temporal correlation. In ASReml, I'll use the AR1V with a single variance and a correlation across time that dissipates as an autoregressive. But obviously, depending on the number of measurements, you can use other models, more flexible, like an exponential for irregular intervals, or some more fixed, like core GH, core H, and so on, in case you have some regular intervals, so you want to do something different. Okay, now, the last thing I want to show before I go to the example is that I mentioned this is linear regressions, but we often have some patterns that are not necessarily linear. So you might have something that goes up and it goes to an asymptote. And in that case, you might need to do some transformation to make the system linear. And that's what I use the word linearize. And often we have a model that describes well, and a transformation, log transformation, exponential transformations will do the trick to make the model linear. You have in the literature different models that are linearized. If you don't want to linearize your model, you can move into something called nonlinear mixed models, but you might not have the same flexibility. So in this particular case, I'm going to use some linearization. When I obtain the BLUP values, I can use them to rank the individuals. And also I can use many other statistics. I'll come back to this slide later, but you can also obtain some statistics that summarize those lines. For example, you want to know the size or the yield at a specific time point. Or you might want to average in a specific window and know, for example, the area under the curve and so on. And you can do some many other things. So let me just go to the example. Actually, before I go to the example, I'm going to describe the data. So this is a public data set from RISE where they try to fit random regressions. This is automatic measurement that they did in a greenhouse genotyping platform, where they took pictures of the plants, so they had the projected shoot area, and they counted the number of pixels that you have from each individual. So this is an approximation of the biomass. Again, it's in just 2 dimensions, but it's an approximation of the biomass. And they did it on days, actually starting on day 12, no, day 13 to day 32. So they did it every single day over 20 days. This is after transplanting, when they put them in the pots, and they had a total of 357 genotype, which is quite a large number, and it allows me to have 357 regressions. Now, the individuals or the genotypes were part of a design in a P-rep design, where a portion of them were replicated with 2 replicates, and in some cases, they only had 1, because they select a portion of the 357 to be replicated, and they repeat that experiment 3 times. So what you see here is the actual data from 1 genotype. You see the 3 curves on the 3 experiments, so that one managed to be replicated 3 times. And you can see the curves are obviously curves. They seem to have risen quite high up, so they haven't reached an asymptote yet. And again, this is only the first few days of the experiment. And I can come up with an experiment with a linear model, a nonlinear model that describes this. This is an exponential model, simple exponential model, where I have an intercept and I have a beta that represents a slope associated with this. Now, if you linearize this by applying the logarithm in front, what you get is the logarithm of y, logarithm of the alpha star, which is an intercept, plus beta divided by xi. So then you have now a model that is linear. You have an intercept, and then you have a slope that is going to be beta, and then you have a new X star, which is 1 over Xi. And then you can fit this. And then this is what you obtain on that same genotype from the other side once you use the inverse of the DAT, which is going to be my X, and when I use the log of Y, which is the yield for this day, in this case, is the PSA or the biomass. So you can see it looks relatively linear, and that's going to be the model I'm going to use. Okay, so let's go straight to some of this. And again, just keep in mind that my objective is to fit those regressions, but for 357 genotypes, and then I need to rank them. Now, I have the data set here, and it has a lot of measurements, and I'm going to only use half of the measurements. So this is day 2, day 4, 6. I use the even numbers on the data set. There's a reason for that I'll explain a bit later, but it's kind of overkill because there's such a high correlation between the day 2 and day 3 and day 4 that I decided to use only half of them. Now I need to add some time because this create my DAT, date after transplanting, and then I have a plant ID, which is the individual plant that was monitored over time, and that belongs to one genotype, and in some cases, as I mentioned, I have 3 copies. So this NSFTV is the genotype ID. I have the experiments, I have reps within the experiment because this is a p-rep, and my PSA is a response variable, and I have divided it by 1,000 for stability. Okay, so here's where you see plant ID, genotype, experiment, rep, and so on, a little bit of the structure of the data, and then just a summarization. So it's elements that where needed to be factors are created as factors, and so on. So a little bit of the data. Again, it's only some of the measurements from 14 to 32 days. And you can see here how the overall means go up, but also the standard deviations of the variances tend to go up, which is very normal for these sort of studies. Plants are growing on size, and then they tend to grow in variability. You can see the means here. The means go from 18 to 392, but also the standard deviations go from 5 to 160. So there's a huge increase on this. And this obviously creates additional complications because it's heterogeneity of variances. So I'm obtaining the means per the means of genotype across all the time, if they have 1, 2, or 3 replications, just to show you how the plot looks when you see the trends of each of these genotype. There is some crossing. Again, it's not very clear because it's 357 genotypes. And I'm just going to plot one. This is the one that I had earlier. And you can see it's broken. It has 3 replications, and it seems to have some variability because in one of the experiments, it had a really good response. Now I do my transformations, so I'm going to apply the model I mentioned to linearize it. So my y, or log of y, is going to be the log of my response PSA, and I add a 0 here, which you don't need to add, but it's to get away from the log of a 0 value. So if PSA was 0, then obviously a log of a 0 value is minus infinitive, and that creates issues. So you add an offset, and something similar with the IDAT, which is the inverse of day after transplanting. I'm adding a constant. In this case, the constant I'm adding is actually 10. So that gives me my transform variable. You can use something different than 10, and that helps a little bit with the curvature of the line so you can see it, okay? So let me just show you again this genotype, how it looks. Oh, I didn't run it, so I need to run that one. And again, it looks very linear. Let me just show you another genotype, 1767. And then this one, for whatever reason, I don't see anything. I might not have any information on that. So, well, let me just put 001. I think I have something with 001. No. Well, anyway, now let me just go back to the one I had. I did have the number. Okay, the 99. I can fit a linear regression on these points. And then I'm just going to write them down, but you can see here the intercept of this genotype is 10.022, and then it has a slope which is minus 174.162. Again, this is just fitting one linear regression to this genotype to all the copies that it has. So what are the other benefits of this transformation? You see very skewed distribution from my PSA. Again, it's many time points, but once you use the log, you get something closer to a normal distribution. The other thing that happens with this one is, remember that heterogeneity of variances. Once I use the DAT, sorry, the log of the Y, you can see the bands are a bit more homogeneous. And again, I'm plotting it here against the inverse of DAT to just show you all the lines, but you can see there that there is something going on. Now I have a few outliers that I'm going to eliminate here, just to show you what we obtain at the end. So when you see those new graphs, you'll see that some of the points that were in the extreme disappear. Again, I did look at this earlier to make sure we have all right. Okay. So now I feel I'm ready to start fitting my models. And this is where things become a bit more complicated because, well, I look at how many observations I have. Notice not many individuals don't have two replicates. And my base model is going to go, as I mentioned before, alpha, which is the overall intercept, and beta, which is the slope. Now I'm going to add an intercept for each genotype, random intercept, and a random, in this case, a slope associated with IDAT for each of the genotype. And this is what I'm doing here. So I go to my model and I have a random intercept, which is the genotype. It's not the breeding value, it's the deviation from that overall slope. And I have that genotype interacting with IDAT, which is my X. Notice that on the numerator or on the fixed part, I have 1 as an intercept and X rep because there is several replicates. There's 2 replicates within experiments. So I have 6 levels there that I need to estimate because all the replicates don't respond the same, the experiments don't respond the same, and so on. And this IDAT is the one that is associated with my original beta. So then that's going to be my slope. Errors are being assumed to be totally independent. The model seems to fit. And now it gives me some variance components. This is the variance associated with the intercepts, the variance associated with the different slopes, and then a residual error. Now I'm going to extend this, and this is where I use this STR, and I say, you know, these levels A and B are actually correlated. So what you do with the STR in ASReml, you put all the intercepts on top, all the slopes in the bottom, and then it is being treated like if it's a single vector, and then you give it an instructor. And the structure, as this is a matrix of 2 by 2 variances, 2 variances, 1 for each of the terms, plus a covariance, and then ID is 357 individuals. So it's going to construct this variance covariance matrix for that. Again, the errors are still independent, and you can see this indicates I need an update. Now you will see this correlation here, and this is a correlation between the regression, in this case, the random regressions of minus 0.90, which is quite high, highly significant. And actually, when I compare this model with the previous one, using the likelihood ratio test, you see that they have quite a lot of improvement. Okay. So slowly I'm getting there. So this is the model I want. I just want to stop for a minute if there's any question. Carrie, do you have anything?
We've got a few, Salvador, but I'm just going to hit you with a couple, if I may.
Okay, no problem.
We have one from Mateus, and he's wondering if the slopes are random, how do we know if the G by E interaction is significant or not?
It will be relatively simple, depends on the model you're using, but in this particular case, for example, I can drop this term totally. If I drop it, I will have a model without the random slopes, and then you can test it. So particularly, I can do it with the previous model. You can do the same thing with the intercepts. You can drop this term, and then you do a likelihood ratio test to compare both models. By the way, if I change this core GH to diagonal, I'm actually having exactly the same model as before. So in one sense, I'm just saying these 2 elements are independent from each other. Okay?
Great.
Another question, Carrie?
Yeah, and we'll take one more. Can you easily explain the difference between random regression and multiple linear regression with interactions?
Oh, yeah, yeah.
Is that a bigger question?
So, well, multiple linear regression has several explanatory variables. So that means several x's. In this particular example, I only have one x, but if you have several x's, you can have age, you can have, I don't know, in this particular case, you might have latitude, longitude if you want to do something extra. So that would be multiple linear regression, but a multiple linear regression normally doesn't have any random effects. It's all fixed effects for just a normal multiple linear regression. In this particular case, I'm saying there is some deviations that are random, so I'm moving into the mixed models, and I'm doing it for a simple linear regression, but I could have a multiple linear regression with random effects for different x's. Okay, so there are different concepts.
Thank you.
Okay.
Guys, we appreciate there's several questions here. If we answer them all now, we're not going to get to the end of the session. So we'll leave them to the end of the session. And if we aren't able to reply to them, as I say, we will come back to them via email. Bear with us. Back over to you, Salvador. Thank you.
Thank you. So now I came back to the slides, and this is the most difficult slide for the whole webinar. Now, when we model random effects for any random effect, we say, for example, blocks are random in an experiment. You're saying that observations that belong to the same level of a block, let's say block 2, are correlated, and you can demonstrate how that correlation occurs. So in some sense, with block randoms, we are modeling some spatial correlation. Now, we also have, in this case, the AI is modeling some level of correlation between the observations that belong to the same level I. So in this case, for the same genotype. Now, we know we have 3 lines in some of the cases. So not all the observations are correlated, but they're correlated because they belong to the same genotype. But if you have only a line, in one sense, this AI is modeling that temporal correlation too with a very simple way, which is a compound symmetry. I don't want to go into all the details. Something similar happens with the beta, that because in groups of observations are sharing the same beta, that means they're going to be correlated in some sense. So what I just want to show here is that I can calculate the correlation between 2 observations that belong to the same individual, the same genotype, belong to the same replicate K, but they're on times J and J prime. So it's like, say, day 2 and day 4, for example. And when you do, you need obviously the covariance between those 2 observations divided by the square root of the multiplication of the variances. This should be a variance. So when I calculate the covariance, obviously the covariance only works on the random effects, and then you have the covariance of the elements for the first against all the observations for the second. Now, first thing, the errors are independent, are going to be independent or not, depends on your assumption. So you can say the errors are independent. In this particular case, I'm going to assume my model didn't model any temporal correlation, so errors are going to be assumed independent. So that's why you have a 0 there. But then you have covariances between AI, BI, BI, AI, and so on, and also with the errors, which are all 0 in that case, so I don't put those. But you can see here that there is a variance of A, there's covariances between terms, so you have a variance of beta times X on one time point times X on the other time point, which are all non-zero. And then 2 times the covariances between A and B, which is the covariance. And this is the sum of the values of time 2 and time 4, which are the x's. So this term here is obviously not 0. This could be negative, and it was negative for us with a negative correlation, but often it won't make this term exactly 0. So you always have something. And because this is non-zero, and it could be positive or negative, that means the correlation between 2 observations at different time points is going to be non-zero, and they are correlated. So you already have some modeling of the correlation. And for that reason, many people just stop with the random regression here, and they say, I know I'm working with time, I'm going to let these random effects model the correlation, and I end up my story there. And you see that a lot on the medical field. However, I'm going to be a bit strict, and I'm going to say, no, the errors are correlated. And this correlation is an autoregressive correlation of order 1 over time. Okay, so I'm using 2, 3, 4, 5, whatever the time points are. It doesn't matter. ASReml doesn't consider them as equally distanced. It doesn't care. It considers them as a factor time. So it takes level 1, level 2, level 3, level 4, and so on. And so that's what I'm doing here instead of using the units. And notice here that I'm using plant ID because I have series of one plant measured 20 times, another plant measured 20 times, and another plant measured 20 times. They all belong to the same genotype, but they are only correlated within plant, not across plants in terms of residuals, because in terms of genetics, they're all correlated with each other, as I just shown in the previous slide. So I'm going to move forward. I need the data to be ordered by plant ID and by time. I'm providing some starting values to this AR1, the same error variance I obtained before, 0.057. And I'm saying, you know, there's going to be a high temporal correlation. So when I do this, if it's, you can do an update. And now you have a few differences. This is the correlation between the A's and the B's. But now I have a correlation on temporal correlation of 0.933, which is very high. And this actually is a correlation that exists between 2 and 4, 4 and 6, 6 and 8, and so on. So it's very high for 2 days. So for that reason, when I did this with 1 day, I had a correlation as big as 0.99, because it's the correlation of day 2 with 3, 3 with 4, and so on. That's a little bit overkill on this experiment because the correlation is very high. The people doing the experiment didn't know that, but this is really telling me you don't really need to measure every day. Every other day is more than enough. And probably you can even test what happens if you do it every 4 days. And this sort of analysis will give you a bit of that. So that's the reason. I can compare this model with the random correlated errors against the original model with the independent errors. And you see the likelihood ratio value is humongous, 18. And this is highly, highly significant. So this is clearly a better model. And when you look at the residuals, and remember I'm using the log of y as my response, it doesn't look perfect. There is still some form of pattern. It's not just like a cloud as we see. And this is due to my model failing on capturing something. It might be that my linear, the equation that I try to fit, when I linearize it, I miss something. Maybe I need a second parameter. Maybe it needs to be quadratic. So in that sense, there is something that possibly is missing here. I don't see it too big, but there is something there. So just to warn you about that. Now, the other thing I need to mention is that sometimes when you try to fit this model with a complex random structure and a complex error structure, it fails. Good to provide some starting values, but sometimes you're asking too much to the data. And I imagine that's why the reason many people decide to use residuals to be sort of just independent and simplify the problem, okay? There is other ways to do it. You can add a random effect of plan ID and we'll take care in a compound symmetry way of some of this autocorrelation. Again, you can simplify things on many ways, but as you can imagine, this gets relatively complex, okay? But I'm kind of happy with my model. I have these lines here just to tell you how we identified outliers, but we don't need to worry about it. But that's going to be my selected model to use, which is I'm going to go to this section now. So I'm going to, again, go back to my model. I just fit it. I seem to be happy with it. It's not perfect, but I can be happy. But my question now is, how do I use the results from this model to make my breeding selection? So there's different things. One of the things that we can do is we can reconstruct the intercept and the slope for each individual. And I'm going to go back here. So what we need to do is I need to identify the overall intercept plus the AI for each individual, 357, and the same thing for the slope, and I can have them together. And from there, I can make decisions. Remember, the one with the highest slope will be probably with the highest rate of growth. So the first thing I do is I get my BLUPs. Notice that I need an intercept, but I need an overall intercept. And the problem with this model is that I have other fixed effects because this intercept is being corrected by being on which experiment, on which rep. You can have many other design effects too. So in that particular case, what I'm going to do is adjust ASReml to provide me with the overall intercept for a value of I that equals to 0. which is again where x is equals to 0, then just provide me with the result. So that's the way. And you have, I have it written down there, you have a value of 9.6633. This is my alpha, overall alpha. I need my overall slope, and the overall slope is here in the I-dat. And so you have now your overall slope is negative minus, it's 162. And actually for that genotype, we just look at, I wrote it down somewhere, we have minus 174 as the overall slope. And then I can get my BLUPs. Now, let me just show you what the BLUPs are. And the BLUPs are for anything that is random. So here I have the random deviations in terms of intercept for the genotypes. And then when I go to tail, I'll show you the last few ones, which are the random deviations of some of the genotypes in terms of slopes. They have different scales, they have different standard errors. Some of them are significant, some of them are not, some different precision, so you can calculate reliability if you want it, because obviously they have different amounts of data. Some of them are replicated 3 times. So that means they are more shrink or less shrink. So what I'm doing here is I'm just creating the intercept, overall intercept plus the A effect, the overall slope plus the B effect. And you can see here in my data frame, something happened here, slope X. What happens with my slope X? I didn't run this line. So here I have my intercept and my slopes. Now I can compare individuals. Oh, okay. So the individual I was looking before, I'm going to just do view. I think it was the individual number 99, was it? Individual, oh, I wrote it down. 99. So I can see the individual 99. It's here. It has an intercept of 9.79 and a slope of minus 164. When I fit it alone, it had a slope of 177. 74. The difference are because we're fitting everything together, and also it's being shrink towards the mean of the population. So, but it gives me a prediction. This is pretty much a prediction of that individual. Now, all the things I'm going to do is you can now you have those lines for each individual. You can do whatever you want with them. So normally in rice, you have a short period, short growth, short duration, they call it. Is rice that you harvest normally after 100 days to 110 days after transplanting. And then you have others 155 or 160. So I'm just going to ask for a prediction for day 100. So I'm going to use 1 over my x plus 10, which is my I-dat. So I'm going to use 100. Now notice that the largest day I have in my data was 32. So this is really an extrapolation. And then I asked ASReml to provide to me for each genotype the actual value corresponding, the value in this case, the prediction. So this is by actually evaluating the regression on this value AHDAT, which happens to be this for the harvest time of 100 days. Okay, now because of all the transformations, you have to be careful to provide the correct X, and also you get some predictions and you need to exponential the prediction minus the constant to actually get the harvest on the units. In this case will be the PSA. And then also I add something extra. You can take the derivatives of your original equation and find where the maximum slope of that equation that I derive is. So I'm providing that here. And I just want to show you a few. So I have many other statistics. I have harvesting, and then I can rank the individuals by harvest, and this is by 100 days. Now, it's a very, very grotesque extrapolation because we only have measurements until day 32, and I'm extrapolating to 100. But if you wanted to use something, maybe you have more measurements, this will give you an option. If you have a biological model or a model that has like an asymptote or something more reasonable and your data covers that, then you can use that, the point of inflection, whatever you want. This is the value at which the highest slope from the current model I have, and you can see it occurs on the day after transplanting between 14.7 and 15.7 if you want to use some of that information. Okay. Now, I'm just saying that extrapolation is very grotesque. So I wonder if there's any question you want to give me now, Carrie.
There's lots, Salvador.
I imagine.
Let's just hit a couple, shall we?
Okay.
So first of all, just from Jared, is it possible to specify random intercepts with respect to two different variables in the same model?
With two different variables in the same model, so that will be like almost like a bivariate model. And the answer is yes. You probably have to create your data set and stack down the traits. It's not going to be easy, but it is possible. And then actually you can even correlate the A from trait 1 with the A from trait 2. So again, everything is possible in ASReml, really. It's just a bit more tricky to get it working.
Sure, lovely, thank you. Another from Fikret. Can you use the length, or in this case ID, to specify the number of levels for the genotype instead of the hard coding, the 357 that was used?
357.
So rather than the genotypes, can we do it for the levels of genotype?
Yes, in this case here, if it's on the predict, yes, we can ask. There is a levels list. I could have put here, I could put here the nsftb.id, and I can say I want the level 1, or I can say I want the genotype nsftb_99, for example. Hopefully that's the question he asked. If I didn't answer, just shoot some more messages, and then I can answer with more time later. Okay?
Yeah, Fikret, if we've misunderstood at all, retype the message or drop me an email. We'll pick that one up.
Okay.
And one more, which I think might be a quick question. She says, is there a minimum number of time points for applying in a random regression model?
Ooh, yeah, it's just like fitting any regression. So if you think about, you have one genotype measure 2 time points, you can only fit the linear regression. So it is 2 time points. You won't have any degrees of freedom, or very little degrees of freedom with 2 time points. Now, if you want to model something much more sophisticated and so on, yes, you need several time points. The problem with this example, it has plenty of time points for the period, but they are too many, too close together. So they don't provide too much information, but I have 10 measurements, particularly on this example. Good. I shall continue so we don't go over the time, okay? There's a few more things that I want to show. I can get predictions for any time point. This is regression, really. So in this particular case, I have this CT, which in reality, I'm asking for a sequence of time points of day 12, 13, 14, 15, 32. You can even ask for decimal places because this is a regression. So I'm doing some interpolation, and I'm doing actually an extrapolation with the 12, but I'm doing interpolation everywhere else. And I can ask ASReml to provide me a value for all of these values of IDAT for each of the genotypes. And it doesn't take too long because the model is not too difficult. And I'm just processing the information. I'm getting here the exponential value of the prediction. And I just give you some of the data I've obtained from this prediction. This has been evaluating the regressions that we have with the model for each of the time points. So you can see here this individual one, you have it from the AT12 to the AT31, and you can see these are the predicted values on the log of the Y, and these are the exponential of those, so they look much more as the way they are in the actual raw data. And then I can use any of these. For example, I can say, oh, let me take the average of the first 7 days. Why the first 7 days, and which is what I do below, is because then that represents the early growth in the first week, and we can see how well it predicts. I can take the last measurement, the time 31 or 32, or I can say what happens if I decided to measure only every certain time points, how the rankings are going to change. Now, these lines are very clear and very highly correlated, so many of the points provide you very similar information. So That is. So let me just show you 3 genotypes. And these genotypes are with the back transform responses. And you can see here, oh yeah, looks fine. 99 is the blue. We have this green one, and then we have the red one. Now I can rank them by looking at the figure. If we had more diversity on this data set, you will see that the lines will cross. Okay, and in this case, the correlation between the A and the B is so high that they tend not to cross. But if you had much lower correlation between those, you will see that some genotypes are better at some time points and others are better at other time points. Also, the differences tend to obviously increase over time or not. So you can do different things. You can use, as I mentioned, time points. You can integrate the area, which will be the area under the curve to make a decision, which is something widely used in animal rearing, for example, milk production, or even chicken number of eggs. If you're dealing with number of eggs as your response, the area under the curve is going to tell you what is the production of that breed of chickens over a certain period. So what I'm doing in these few lines, I'm just decided to take the average of the first 7 observations, so days 12 to days 18, because I think that's early growth, and I want to see how early growth correlates probably with the total final growth of 32. I know there's a few questions that I'll just move a little bit with this, and then I'll start for more questions, okay? And here you can see the average. So I'm just getting the average of those observations for each of the genotypes. And actually in the next line, what I do is I'm just ranking from the highest to the lowest, okay? So we have 38. The value doesn't mean too much because it's the average of the first days. But you have a value that allows you to say, oh, 39 seems to be considerably better than anyone, all of those over this first week. So it gives you some more details. I could also use the date of 32 just to see how these compare. And this is what I did here. And you have, let me just show you this. This is the line where I'm ranking the individuals according to the mean of the first 7 days. And this is the ranking of the individuals according to their response at day 32. And you can see 2, 34, and 39 are also on the top, but they swap positions. Okay, so it gives you a little bit of a different thing. They swap positions on the averages because probably one went overall on the 32, and so on. You can try to calculate standard errors. It's not very easy, but it's possible. And you can use those to kind of create different indexes for different things. So obviously for different periods, define different products for your breeding, and so on. And the final thing I was going to show you is what happens if I only analyze the data from day 32. Okay, and this is just a very quick thing. So again, I just filter for the day 32. I'm not going to use any transformation or anything. I just fit my model with the day 32. Again, I have the rep within experiment. I have the genotype effect. And I'm going to use a residual errors that is different by experiment. And this is because I'm suspecting the experiments have different variances. Now, the residual plot looks, when it comes, relatively okay. Again, it's by experiment. So let me show you a few things. This is just a normal plot. You can see here, there's a few potential outliers by experiment. There's one here again. And then when we look at the distributions of them, there's potentially something, but they look very good. So you can mostly assume that they have approximately normal distribution. The variance components are here. This is the genetic variance. And these are the error variances associated to the different experiments. And you can see here, they change quite a bit. So one of them is more than double than the other, and that's why it's heterogeneity. And I can calculate a heritability. Notice that in the random regression before I didn't calculate a heritability because it's not very easy. Again, we are dealing with a regression. So you almost have to say, do you want the heritability for which day? And then from there, you can try to calculate or approximate some formula. Not very simple, but it's still possible. In this particular case, it's telling me that the heritability at day 32 is almost 0.6, so that's very good. And then I can get my predictions of the genotypes. So this is the prediction of the genotype on day 32, so what their value is. And you can see here the ranking of those, and you again see very similar results, 39 and 234 and 369. So this analysis with the previous analysis that I did when I only show you the values from 32 is not very different. The values are a bit different because of the shrinkage. Ooh, they look quite different. Well, because this is, there are different transformations. So then when I do those correlations, the correlation between those two is 0.98. Here they look a lot better. I don't know why the values were so different. So that's probably the 7 days. So you see the correlation between using everything and using just 32 is relatively high. There's some individuals that change, maybe because they have issues on age 32 and so on. It's possible to fit some models that are with different splines. Splines is a lot more flexible and allows you to have a polynomial joint regressions without specifying what are the points. It's widely used in animal breeding where you don't have like a regular trend. So each animal, or in this case, each genotype will have its own cubic spline. You can fit the same thing here. I'm doing it using the original response variable. And notice that here I have a spline associated with DAT with 5 knots. I'm not going to go into details. I just want to show you that you can also do it with the splines. I'm not correlating these terms, and I'm doing AR1, but in this particular case, I'm using an heterogeneous errors because I'm using the original response PSA. If I use the log of PSA, I would probably use just common variance. And again, it's just to show you the model. It's a bit more difficult to fit because of all these elements. I'm using 5 knots. You can change that to 10, 15. Remember, I only have 10 observations, so there's not much point to put too many knots. And you can see here the variance components. This is the correlation, the temporal correlation, very high. The variances increase quite widely because I'm using the original response, and some of the variances associated with the intercepts and associated with the coefficients of the spline. Okay, and then just to show you the predictions of a few genotypes, you'll see the same 3 genotypes from before, and the curves look quite different. And again, it's different assumptions. They tend to cross more. This model is not being purified or adjusted for anything. I just wanted to show you that you can get, you can use different approaches. You have splines, you have polynomials, you have Lagrange polynomials, or you can create your own specific elements. Okay, so with that, I think I finished. So I'm open for questions in the next few minutes.
Thank you, Salvador. Couple of questions, lots of questions. I'll take a couple here. I think you touched on this, but when you're dealing with nonlinear curves, why do we not just use higher polynomials instead? So, you know, why do we linearize rather than modeling the nonlinearity?
It is possible to linearize. You have to be careful. The higher order polynomials ideally should be orthogonal, or at least your x's should be center to eliminate some of that collinearity. But the reason why we want to use some other models is because the coefficients have more interpretation. So in this particular case, the beta parameter, it's actually associated with the slope, and you can use it. The exponential of a, the intercept, or a alpha plus a, is actually associated with the asymptote. So depending on the model you use, some of the parameters have quite a nice biological interpretation.
Great, thanks. I'll take a question from Eric here. He said, when fitting a model with observations too close in time, it can lead to numerical problems with too high temporal correlations. Likewise, problems can be anticipated with high negative correlation between intercept and slope. Would it be a case, or would it be sensible to center or zero mean the time regressor to avoid design-related correlation between slope and intercept? I feel this is probably a discussion rather than a question.
Yeah, but I'm not sure about the tricks between, well, yes, I mean, you can change if you divide x by 10, you change the slope and you're going to change the correlation. The correlation should stay the same, but the elements are more stable. The way I like to see it, if you have the variance of A to be 0.00016 and the variance of B being 2,368,000, whatever, obviously the scales are so different that makes the covariance very unstable and therefore the correlation. So if you divide your X by 10 or multiply by 10, sometimes you get those elements a bit closer. And that goes for any multi-trait analysis that you do too. Now, the temporal correlation is a bit more tricky because the temporal correlation sometimes is also unstable. And if I was measuring things every minute, then the correlation will be probably 1. Because it oftentimes are so close together that, one option is to use just less measurements, or sometimes, for example, in order to reduce the high level of correlation, like in this case, maybe I use day 2 and 4, and if I have multiply everything by 24, or divided by 7, I will have the value by week, or a fraction by week. And sometimes that makes those correlations a little bit more stable, okay? It's like changing the time from minutes to hours or to days, okay? Good.
Thanks. Okay, one more, hopefully it's quickie. So what would happen if the time points aren't equally spaced?
That's not a problem at all. What I didn't explain here is, for example, in case of example of chickens where you have the production on the Y, chickens sometimes don't produce eggs one day. Or sometimes when you measure them, you measure over a period or in specific days. You don't have to go every single day. So in that case, in terms of regression, just that means that your points for one genotype are different than the points from the other genotype because they're not in exactly the same time points. But what it does change is your temporal correlation. You cannot use an AR1 because, again, the time points are not equivalent. In that case, you're better using an exponential or a power. And that solves the problem. Okay?
Great. Thank you. As I say, lots more questions, and we're going to get to those by email. If you've registered with your email, if you haven't registered with your email and you want us to send the details, the slides and the recording, please contact us. It will also be uploaded to YouTube within 2 or 3 days maximum, and we'll send you all the resources as well. We knew this was going to be a challenging subject. There's been an awful lot of questions. I think perhaps we're going to do a part 2 to this, or maybe we'll open up a bit of a question and answer session, but I'll let you all know on that one. Thank you for joining. Bear with us, as I say, everything will be sent to you within a few days. Thanks for your attendance. Thanks for your very interesting questions. And yeah, you will hear from us shortly. And thank you, Salvador, as always.
Nice to see you, and see you next time.
See you next time.